So welcome everyone. Thanks a lot for being here. Thanks for joining. And today, this should be the fourth lecture. It should be the fourth lecture that will complete this very short series. And yeah, we can have more in the future. So if you're interested, yeah, let's keep in touch. And yeah, so what about today's lecture? In the previous lectures, we mainly introduced the different concepts. We talked about the different definitions and the properties of the definitions. We may need to do a little bit more today, but also we would like to get to some calculations today. So we will do some calculations related to transforming distribution functions. If you define one random variable in terms of another one, let's say for continuous random variables, you may want to understand what the PDF of the new random variable is. So yeah, those kind of computations we will do today to illustrate the concepts and to show how it kind of fits together. Obviously, there will be many things left out. Probability and statistics is a huge field. But in the future lectures that hopefully can take place, we can go to the more advanced stuff as well. So if you just follow these 4 lectures, what you should get out of this is some solid understanding what the main mathematical objects are, how they are defined, and how to work with some of these at the level of calculations. So there will be also a 4th quiz following this lecture. And I would also want to issue some homework. If you are willing to do homework, that's awesome. So this will be some homework using Jupyter notebooks and some coding and things like that. All right, so I think maybe I should share my screen here. Yeah, just a brief reminder. So if you did not sign up for the quizzes and the homework, you can do that using this particular sign up link that you see here. I guess the number 3 that also belongs to that link. And yeah, what did we do the last time? Actually, before that, I may want to check some messages here in the chat. Can we get the link of recordings to previous 3 lectures? Yeah, so the links are posted on the Machine Learning Tokyo website. But also, if you just go to YouTube and you Google MLT probability theory, maybe including my last name, Fabinger, you should be able to find that. And yeah, so if people are also willing to do this homework using Jupyter notebooks, that will be awesome. You will be able to get feedback on that as well. So yeah, maybe some really brief recapitulation. I think there's a lot of stuff to be discussed today, but I just want to remind you of what we did. So the last time we focused on random variables, and we said that a random variable is a function. We included all of the technicalities in here, but really the main point was that a random variable was a function that would be taken as arguments different element of our sample space, so the different outcomes, and it would produce a real number. So we talked just about a scalar real random variable. That's what we mean by a random variable here. Obviously, you can generalize that. And yeah, we had some examples. So this was a quick example of a random variable that was just a quadratic function where the functional value was just omega squared, where omega was the outcome. In this case, the outcome was just a real number. I'm not going to repeat here the technicalities unless people ask me about that. And we talked about distributions of random variables. So what is a distribution of a random variable? A distribution of a random variable is this px in the case of random variable x. And it's basically the assignment of the probability to different regions to which the random variable x may belong. So yeah, for us, the random variable x would take as functional values individual real numbers. And if you imagine some region, some subset of the real line, you can ask what is the probability that x belongs there. And yeah, this kind of probability for us was denoted px of b. And px is simply the distribution. So the distribution is a function that for regions like this will give you the probability. Now, there was a technical condition there. We wanted this b to be an element of the Borel sigma field. But yeah, I'm not going to emphasize the technical aspects in this recapitulation. But one thing that I should mention here is that the distribution, when it's defined, is by definition connected to the probability measure p that we started with. And specifically for the region B, maybe an interval to which x can belong, we can look up all of the possible outcomes omega such that x belongs to B. That was this pre-image x inverse B, and we would look up the probability measure of that. And that would give us the distribution of x evaluated for this set B. Now, yeah, again, this sounds a little bit complicated, but basically what you are doing here is you specify some region or some range to which x should belong. Then you look up all of the possible outcomes that are consistent with x belonging to that set B. Then you look up the probability measure of that set. So this is some subset of the sample space. And you say this is going to be the functional value of the distribution evaluated at B. Yeah, any questions about this? So if people are okay with this, then let's remind ourselves of some other concepts. So very important is this cumulative distribution function. And the cumulative distribution function was defined simply using the distribution of x. Specifically, we say that the functional value at point little x of this cumulative distribution function of the random variable x is going to be this distribution evaluated for this interval from -infinity to x, including x. So yeah, this right-hand side here simply is the probability that the realized value of capital X is going to be less than specified value little x, and that's the CDF. So yeah, the CDF at little x is the probability that the realized value of capital X is no greater than little x. And yeah, I think we will have some pictures also. Okay, I'm getting a question. Can you give an example of the distribution? All right, I have some pictures of CDF, so I think I should use that. Let me see. Yeah, why don't we look at this picture here? So this was the CDF of the Bernoulli. This was the CDF of the binomial distribution. A binomial distribution corresponds to a certain number of coin flips for a coin that may not or may be a fair coin. And yeah, you would count the number of heads. So I think in this case, we had 10 coin flips and it was not a fair coin. And we would count how many heads we obtained. The red dots here indicate the probability of the different counts. So for example, this height here, that was the probability that you get precisely 7 heads. And the CDF that was indicated here in blue. And yeah, let's say you choose as little x this value of 7.5. And the height of the line that I just drew, that is the probability that when you randomly get a draw from this distribution, the value will be less or equal to 7.5. So that's an example of a CDF. And what would be an example of the distribution? Well, for the same phenomenon that we have here, say for the coin flips and the counting of the heads, you can ask questions like, what's the probability that I'm going to get the number of heads somewhere between 4.5 and 7.5. So you include these possibilities. The realized values here corresponding to this region B, that would be 5, 6, and 7, 5, 6, and 7. And yeah, the distribution here is simply the probability that the variable x ends up inside this region capital B that I just drew here. Okay, let me see if I answer the question well enough. So a question, just a small confusion. Whenever we talk about distribution, are we talking about CDF or are there distributions that are not CDF? Okay, so yeah, it's a good question. It's kind of terminologically difficult because really, technically, if we strictly define the terms, by distribution, we mean this concept here, so the P of x. So the argument of this function, P of x, is going to be a set. It's going to be a region or set to which x can belong. And the function gives you the probability of that set, the probability of x belonging to that set. Now, informally, when people say distribution, they can mean all sorts of things. So that creates the confusion in here. So when people say distribution, they can mean the probability mass function, they can mean the probability density function, they can mean the cumulative distribution function. Basically anything that uniquely determines the distribution. So if you give me the CDF of some variable, then I will be able to tell you what this function Px is. But technically, the distribution is supposed to be a distinct concept from the CDF or the PDF or the probability mass function. When I say distribution, I can mean all sorts of things, but like strictly the definition really is supposed to be this function Px. So any more questions about this? And then, once we have the distribution, we can introduce the cumulative distribution function that simply measures this probability I just talked about. And I also mentioned different types of random variables. I said that you can have discrete random variables. So these discrete random variables would take values in some countable set. So the set can be a finite set. The set can be infinite, but if it's infinite, it should still be countable, meaning that the different possible values of x can be written as some infinite sequence. So if you can do that, then you call the random variable discrete. Then we can have also continuous random variables, and that's something that I want to elaborate more today. So I want to provide more general view of these continuous random variables than what we had the last time. And also the calculations that we will make, they will be related to continuous random variables. We will look at transformations of probability density functions. Oh yeah, now that I think about it, I think the last time I didn't emphasize 2 points. So points of caution. So the term continuous random variable can be confusing. Yeah, the continuous random variable x does not have to be a continuous function. Okay, so the continuous, when we say continuous random variable, it has something to do with the distribution of it, but it's not so closely related to the shape of capital X. So yeah, continuous random variable does not mean that x of omega is a continuous function of omega. And also the probability density function does not have to be continuous. So something to keep in mind. Yeah, I mentioned that you can also have these singular random variables. They will not be important for our practical application, so we are going to ignore them. They are like a mathematical curiosity. And we can have mixtures of distributions, so they are important. In the first lecture, I talked about the mixtures of discrete and continuous random variables. Then, yeah, as for discrete distributions, you can have the probability mass function, and the probability mass function simply gives you the probabilities of these individual values of the random variable. So for example, if you have the Poisson distribution, the probability mass function would be indicated here using the red dots. So the height of the red dot, that's the value of the probability mass function of this Poisson distribution. And yeah, if you ask for the probability mass function at other places, at values that the random variable just cannot take, you can say the probability mass function is equal to 0 in there. And then we are getting close to the main subject of today's discussion. Probability density functions. So probability density functions, they will be defined for the so-called continuous random variables. I'm going to elaborate on that, but let me remind you here of some simple case that we had the last time. So what's the simple case? The simple case would be where the CDF of your random variable is differentiable. So it has derivatives everywhere. So in that case, to define the probability density function, all you need to do is to take the derivative. You can denote the derivative this way. You can denote the derivative this way. It's the same meaning in here. And yeah, I have some picture here of the CDF and a PDF of a distribution, specifically of a normal distribution. And the last time people asked me about the reason for taking the derivatives in here. So I would like to elaborate on it a little bit more. I have some visualization here. And once we have gone through the visualization, we can also get to some new material. Yeah, so what is this picture? So this picture corresponds to a random variable that follows the normal distribution. I think I didn't write down the formula for the PDF of the normal distribution. So it's this one. So this is the PDF of the normal distribution. And it has 2 parameters. One of them is mu, that's the mean. One of them is sigma, standard deviation, that tells you how spread out it is. So in this visualization, we can adjust these. We can change the mean of the distribution. Okay, sorry, I think I need to enable dynamics in here. So yeah, we can change the mean of the distribution. We can change the standard deviation of the distribution. And the curves that you see here, they are representing the PDF, that's the green curve. and the green plot, and the CDF, that's the blue one. So if you think about some particular value of x, let's say 4.5, that's indicated here. The value of the CDF there is this height. So if the CDF is this much, it indicates the probability that a randomly drawn value of x is going to be somewhere in here. So from -infinity to this chosen value of x, inclusive of x. So that's the height of the CDF. And yeah, what about the relationship to the PDF? The PDF is supposed to be a probability density. So it tells you how likely the value of x is in some small chosen interval. So if the height here is high, it means it's more likely that in some small interval around that, the realized value of x will show up. And yeah, so I want to say that the area under the curve that's indicated here with green, that's the total probability that x is going to be somewhere between -infinity and this chosen value of x. Or to elaborate on this a little bit more, let's think about changing the cutoff. I'm calling this cutoff, sorry, I'm calling this cutoff x1. I can change that. So if we move x1 by a little bit, then the CDF also goes up here, right? So of course, relative to the previous value, sorry, relative to the previous value that we had, the CDF is now higher. So the difference in the height, which was something like this, the difference in the height, that's indicating how much more likely the realized value is going to be below x1 if we shift x1 by the specified shift. Okay, I think I may want to draw a couple more lines in here. So this was the original height of the CDF. This is the new height of the CDF. Sorry, including this part, that's the new height of the CDF. The difference is indicated here. And what's the interpretation of the difference between the two heights? It's simply the probability that the random variable ends up somewhere between the old value of x1 and the new value of x1. And if you chose this this interval very short, then approximately the slope of the CDF is going to be equal to the height of the PDF in here. Or in other words, the probability that your random variable x can end up somewhere in this range can be expressed in two ways, approximately. One way is the change in the height of the CDF. The other way is the probability density function multiplied by the interval in here. So this height times this base. And that approximately is really the area under the curve. Yeah, the conclusion here will be that the probability density in here is going to be approximately equal to the change in the height of the CDF divided by the length of this interval. Maybe I'm saying something already obvious, but I just wanted to elaborate on this a little bit. All right, so again, the area under the curve up to this value x1 is equal to the CDF at that point x1. So yeah, any questions? Then this was the simple case. Let's get to a more general case. Now, why would we want to consider something more general? It's simply because the PDF, it can have maybe, well, the PDF can be discontinuous, and we may want to be able to handle things like that. So what's the general case? If you have, if you want to define what it means to have a continuously distributed random variable, we can start with this formula. So resembling our discussion with the integral. But yeah, let's assume that the CDF, capital F, can be written as an integral of something. So it will be an integral from -infinity to this lowercase x. And it will be an integral of a function that we can call f of x, or like a lowercase f. And this function is going to be called the probability density function. So instead of starting with derivatives, we are starting here with an integral expression. So if the CDF is an integral of something, then we say that this random variable x is a continuous random variable, or it's continuously distributed. And we say that little f is the probability density function. It's a bit more general definition. Because maybe the CDF does not have a derivative at certain places. And that's actually perfectly fine with this definition. Now, technically, what is the meaning of the integral? For us, it will be the Lebesgue integral. If you haven't seen measure theory and the Lebesgue integrals, we can definitely cover that. We already have all the mathematical machinery that we would need to define Lebesgue integrals. So maybe in some future sessions, I could do that. We already have the main concepts that we need for that. But for now, let's just say that we have some way of defining integrals, and we use that here. So it will be the Lebesgue integral. All right, I think I have a lot of things to say here, but any questions at this moment? So one thing is, if we have this definition, then the PDF is not unique. If you modify the PDF at just one point, then you are not going to change this integral, meaning that you can have multiple candidate probability density functions, and they all can be correct. They all can correspond to the same CDF. So just a quick point. If you modify f(x) at a finite number of points, or in general, measure zero set, so-called measure zero set, you are not changing the integral. So if it was the PDF before, it will still be a PDF. And a question, what is the integral from -infinity, not zero, for instance? It's simply because we need to take into account all of the possible values of x that are below a certain specified cutoff. Do I have pictures here? Oh, maybe let me switch here. So in this particular visualization, we have some cutoff. And we have the value of the CDF in here. And it corresponds to the probability that x is below this value. And it can be anywhere below the value. So it can be in negative numbers. And then the value of the CDF is going to be the integral of the PDF all the way from -infinity to this cutoff value. So if you started the integral from 0, then you would not be computing CDF. You would be just calculating the probability that x is below 0 and this cutoff x1. All right. So hopefully this is clear. What would be an example where we need this more general definition? I have some pictures here. So I have a picture of the Pareto distribution, and this one it has a CDF that looks like this. The CDF is constant; it's equal to 0, all the way to some place that you like. So in this particular case, it's number 1, and then the Pareto distribution CDF starts going up. Let me get this right. Yeah, so the CDF starts going up. So in this case, you don't actually have a derivative at this one point. So we cannot use the simple definition of the PDF, but the more general definition is just fine. You can find this function, the other one, the beige curve, such that the integral of this is equal to the CDF. And we have some meaningful probability density function in here. And then if you want to understand the relationship between the more general definition and the more specialized definition, well, in the specialized case, we were assuming that capital F is differentiable. So this was supposed to be Fx in here. And you can take just this defining relationship. You take this, you can take this defining relationship for the CDF, for the PDF. You can differentiate the left-hand side, you can differentiate the right-hand side, and you see the previous relationship we had before. So yeah, the PDF here is going to be simply the derivative of the CDF. So this was assuming that the CDF is differentiable everywhere. Okay, another question, how does one interpret the values of a PDF greater than 1? Well, as for the PDF, it doesn't matter. So the range of the functional values of the PDF is not restricted. It can be any number between 0 and plus infinity. And the thing that cannot be greater than 1 is the CDF. And that's just fine. So in this picture that we had here, the blue curve was not above 1. So we have things normalized just fine in here. So yeah, if you have a PDF with a very high value, it simply means that the values of X around that place are quite likely. Okay, so this was actually some more technicalities in here, but I wanted to get to calculations as well. Let me see. So anything else I should emphasize here? I think I said what I wanted to say here. So yeah, let's jump to calculations. Okay, another question. What is happening if a blue and red curves are crossing? So yeah, that does not have actually any special meaning if you are talking about these. So in some sense, the units in which you measure the PDF and CDF, they're going to be different. Yeah, let's say that you have some other variable, some other random variable that indicates temperatures. So in that case, what's the unit of in which you measure the CDF? The unit will be just plain dimensionless units. So it can be number like a 0.5. If you are talking about the PDF of temperature, it's not going to be dimensionless. The PDF is going to, the PDF is going to have the dimension of 1 over temperature. So the units in which you would measure the PDF is going to be 1 over Kelvin, for example. And for that reason, because one variable is dimensionless and the other variable is dimensionful, it's actually not a meaningful thing to ask what happens when they are equal to each other. If you change the units in which you measure things, the point where these things cross is going to move. Yeah, so great question. Thanks for that. This is good to clarify. And yeah, so why don't we jump to computations? I don't have actually that much time. We would like to ask what happens if you define a new variable in terms of an old one. And let's say both of these are going to be continuously distributed random variables. You have some variable capital X, and you have some new variable capital Y. And these are related by some function that you specify, function little g in here. This situation shows up everywhere in statistics. And if you think about, say, high-dimensional random variables, this can be, for example, this function g can be, for example, a neural network. If you think about generative adversarial networks, that's a concept that's very interesting in machine learning and deep learning. Then you can have some variable x that's drawn from some completely random distribution that you specify. And your neural network G can produce some other random variable that can have very interesting properties. It can be an image, it can be a photorealistic image, it can be something like that. So if you want to look at the math related to, say, generative adversarial networks, you probably also need to understand the kind of math we will discuss here. Yeah, if you're not familiar with GANs, generative adversarial networks, don't worry. But for those of you who know them quite well, I just want to emphasize that this style of computation is something that's relevant there as well. It's more complicated because these variables x and y can be high dimensional, yeah, basically generalizations of the kind of formulas that we will see here apply there as well. Okay, so yeah, let's just think about something simple. We have one real number, capital X in here. That's going to be the random variable for us. We have some function. We have a new random variable. And we want to understand what happens to the distributions. Before that, I would like to set up some notation. So for simplicity, let's assume that this function g actually does have an inverse. So the inverse of that function will be this one, g inverse y, that will give you the value of x. If it doesn't have an inverse, then we need to split the different regions of the possible values of x into different pieces. But yeah, let's just focus on this one case for simplicity at the beginning, where g is invertible. And then, yeah, we can ask for the PDF. Actually, for the calculation, I would like to make this assumption. For the pictures, I have the more complicated case. So let me switch here to some visualization, dynamic visualization. And yeah, this one is slightly more complicated because the transformation function g that I chose is not invertible. So this one is going to be a quadratic function. And I probably need to explain exactly what's going on in this figure. It looks pretty complicated. Yeah, first of all, we will have some possible values of x. We will use the horizontal axis for that. We will have some possible values of y. We will use the vertical axis for that. Then we have some distribution of x that we start with. So that's indicated here by the green curve. And the green curve indicates the probability density function. Probability density function of x. Yeah, specifically in this visualization, this is a normal distribution. we can change the mean of that particular normal distribution. So we can shift it around, we can change the standard deviation, and so on. Then what about the random variable y? How is that defined? Well, the function g is indicated here by the blue curve. So this function is simply y equal to x squared. That is, for example, here when x is equal to 2, we just square it, we obtain number 4, and that's going to be the value of y that corresponds to that x. And the blue curve here is a parabola. It's the plot of y equal to x squared. And finally, the last curve that I have here, the red one, that's supposed to indicate the probability density function of y. But it's drawn kind of in a complicated way. It's drawn in an unusual way. I'm using the vertical axis here to indicate the values of y. And I'm using basically this dimension to indicate the different values of the PDF. So it's a little bit confusing figure, but hopefully you understand. So if these values of x are likely, then these values of y are likely. And we can also show here how the different values are related. So for a particular value of x, you can look up the corresponding value of y. And if you want to make a calculation of this new PDF, we need to take into account the fact that maybe a relatively short interval of x can translate into a relatively long interval of y, or maybe a long interval of x translates to a short interval of y, depending on where you are. So you see it kind of here. So for these values, you can ask, what's, for example, the chance that x belongs here to this interval? It will translate to the probability of y belonging here. If I shift this around, then even if I keep the range of x's constant, the range of y's is going to be changing. So here, for a particular range of x, we have short interval of y's. If I go somewhere here, we get a long interval of y's. So that's something that we need to take into account. If you have the interval of y's, the range of y's in here are very short, then whatever probability you had in here of x's, that's going to get compressed. So that's going to lead to high values of the probability density function. If instead you have here relatively long range of y's corresponding to your specified range of x's, then the possible values are going to get more spread out, and your probability density function is going to be smaller. So the probability gets more diluted. And I think I would like to show you here some calculations that allow you to do this transformation. Now, looks like I don't have actually that much time. So some of these I may need to leave in the notes, but let me at least explain how the calculation works. Before that, I may also want to move these distributions a bit. So you see, if I move the distribution of x to low values, those will be the places where the small intervals of y are going to be very short. So the probability is going to get more concentrated. If I move the original distribution of x to higher values, where we get these larger ranges of y, the probability is going to get more diluted, and we will have smaller values of the probability density function in here. So yeah, definitely I want to show you the equations, and the homework will be also related to this, but before that, any questions? Okay, so one question here is the area preserved under the quadratic function as area of the curve gives the CDF, and they look like normal, just with different mean and standard deviation. So yeah, the PDF is actually going to be quite different. It's going to be a very different function. And the thing that gets preserved here, or the things that correspond nicely between x's and y's, those are the values of the CDFs. So that's where we'll start the calculation. But before I show you the equations briefly, let me also move the curves a little bit to make the point. So now, yeah, let's get to the equations. Yeah, the new distribution definitely is not going to be a normal distribution. And yeah, I want to make the following claim. Let's say that we have a function g that is just increasing, and the derivative of g is positive. Then the new CDF is going to be given by this formula in here. How do we derive that formula? Well, actually, maybe I should comment here on the intuition. The denominator in here that you see that will be related to the probability compression effect that we talked about, the dilution or more concentration. And yeah, as for the derivation, it's actually not terribly complicated, although there are quite many pieces of notation to introduce. We start with the observation that if g is increasing, then the probability that x is below a certain cutoff must be equal to the probability of y that's being below the cutoff that precisely corresponds to the value of x. So the CDF of x must be, the CDF of x must be equal to the CDF of y if we choose the right arguments. And specifically, if the value of y is the transform value of x, so g of x, we have this equality in here. So that's the main observation. Everything else is actually just a simple consequence of this equation. And yeah, so again, if you have corresponding values of x and y, then if x is below your specified value of x, then y is below your specified value of y. Now, if things are differentiable, we can differentiate both sides of the equation. So we can write it this way, we can write it this way. And then on the left-hand side, we recognize the PDF of x. On the right-hand side, we have a little bit more complicated expression, but yeah, we can use the chain rule of calculus to evaluate that if everything is differentiable. We are going to get the derivative of the outer function times the derivative of the inner function. At this moment, we recognize this f prime as the PDF of y. So suddenly, our equation really gives us a relationship between the PDF of x and PDF of y. And yeah, this g prime plays an important role in here. If g prime is positive, we can divide by it, and we have this expression. And that basically is the transformation formula that we wanted to get. Now, you can make some cosmetic changes to the transformation formula. You can say that instead of x on the right-hand side, you would like to write g inverse y. So the value of x that corresponds to y. If you do that, you get this formula right here. So that's how you can compute the new PDF. Things are different slightly if G prime is actually negative. So if G prime is negative, you get one extra minus sign. You will see that in the notes. Basically, we start with a slightly different formula, this particular relationship between CDFs. So it gives us an extra minus sign, but otherwise the derivation would be exactly the same. And the two results that we have here, one for G prime positive, one for G prime negative, they can be summarized. They can be summarized by a formula like this that contains an absolute value in the denominator. So yeah, the PDF of y is proportional to the PDF of x at the corresponding point. But we also have this denominator that's responsible for the compression or dilution. Now, I realized I'm saying things maybe a little bit too fast. Maybe I was a bit too optimistic. But let's take a look at what the formula produces if we have some very specific distributions in here. So let's say that we have y equal to x squared. That's exactly what we had before in the picture. And yeah, in that case, G prime is 2 times x. Now you have to think about the positive part and the negative part. So part where x is positive, part where x is negative. And you need to do this calculation separately for each one of them. For the positive part, we get G inverse like square root of y. For the negative x part, we get minus square root of y. So I'm just inverting this function x squared. So if you calculate the derivative, if you calculate the inverse, in general, the value of the denominator that we had is 2 times square root of y. And with this, we can try to plug things in to the formula. So if we have a normal distribution, the normal distribution PDF looks like this. And for simplicity, let's take the standard normal distribution. So mu equal to 0, sigma equal to 1. Well, in that case, the PDF simplifies. It's this formula right here. And yeah, we can also plug in for x. Yeah, now that I think about it, oh yeah, this is fine. So this will be the correct value of the PDF. So this was the expression for the numerator. And we conclude that the contribution from positive x towards our formula is this one. So you would obtain that by taking this numerator and dividing by this denominator. Yeah, this is contribution towards the PDF of y from positive x's. We also have negative x's, and they contribute equally because everything is symmetric here. So we basically have two contributions towards the PDF of y. And if we sum them up, we get this formula right here. Now in the formula, I'm assuming y is positive. If y is 0 or negative, then yeah, we can say that the PDF of y in there is equal to 0, right? Because y is a square of something, it cannot be negative. So that's the result of the computation. Maybe I should not have attempted the computation here because we had too little time. But yeah, let me point out one more thing, which is that yeah, the transform distribution has a name. This distribution of y with this particular PDF is the so-called chi-square distribution with 1 degree of freedom. Yeah, computations of this kind are actually pretty important if you think about linear regressions and yeah, maybe some similar type of calculations in statistics. So if we get to more advanced parts of statistics, you will actually see these kind of distributions again. Here, I just wanted to provide a quick example that is both relatively straightforward to follow and also has some practical significance for practical computations in statistics. Now I realize this was too quick, so you will have the notes. You will be able to take a look at these equations in here. And yeah, if I didn't get the visualization exactly right, I think I may need to replace that part. But yeah, this was some example of where you can use these PDFs to say something interesting about, or where you can use CDFs to say something interesting about PDFs of transformed variables. So thanks for joining.